Colleagues and friends, thank you very much for introducing myself, Andreas. I'm going to take you through maybe 450 years of history first of mineral predictive mapping, starting here in Saxony in the year 1556 by the famous book of Agricola, summarizes the knowledge and intuition at that time about mineral prospection. Up to the current day situation where we are using AI technologies. Our company started to use these technologies about 20 years ago for mineral predictive mapping. So we go through this history quickly and also through 20 years of our company history and finalizing with an outlook what we are going to do in future in these fields. So 150 years after this book of Agricola, the first geological map was created again here in Saxony by Carpentier in the year 1778. And the much better English geological map was then created by William Smith in 1814. Now, metallurgy, how to search for minerals, for commodities. The big step ahead was the birth of metallurgy in the year 1913 by a French guy, Louis Launay, who identified metallurgy as a science studying mineral deposits in the environment of their geology. So the geology guides to the deposit. That is the sense behind this. And in the 20th century, metallurgy and metallurgical maps became a common matter of looking for minerals. Here we have some of these maps. And then we need the understanding of how mineral deposits are formed. And here a big step ahead was this research from Garros and Christ from the United States in 1965. They published the book Solutions, Minerals and Equilibria, summarizing the knowledge about formation of hydrothermal deposits. And then we have the exploration models. So it's our sketches or schematic models summarizing the location or the location of a mineral deposit in its geological environment. Here we have an example from Tin in the Erzgebirge with some of the models developed in the 1980s, 1960s. Now about the data. Today we do have a lot of data. Here we have example from the geological map and geophysical potassium map of Nigeria. For instance, the potassium map, yes, showing how the pointer. Here's the pointer. How these potassium-rich basement rocks are transporting materials to the basin. You see this alluvial fence. The next, this wasn't this. Okay. So geological maps. Geological maps carry a lot of information about faulting, ages, lithologies, foliation. And out of these maps, a lot of information can be extracted, very important for mineral predictive mapping. Another type of geophysical maps is electromagnetics, informing us about the deeper structures. Here again, this piece of Nigeria, and we can guess here somehow these faults in these lines here expressed in the second and the first gradient, first derivative of the magnetic field. Geochemical data, geochemical maps from the Erzgebirge created about 10 years ago in the course of the Wisdom Earth project. The shape of the Earth, geomorphological maps give us information about the presence, for instance, of placer deposits. And remote sensing data, optical remote sensing data. Here, Sentinel-2 data with a spatial resolution of 10 to 60 meters with different bandwidths of the light and derived information. So we see we have a lot of information. We have exploration models. And now we need to bring it together, how geologists did that over the years. They were analyzing the data, having an understanding of the formation principles of the existing deposits, and then they created these exploration target maps by use of different supporting instruments in the later years, computers. And now we replace this guy here by algorithms. But first, let us please have a look at the term mineral prospectivity, what it is. Mineral prospectivity, according to Carranza, refers to a chance or likelihood that mineral deposits of the type sought can be found in a piece of land. And the mineral prospectivity cannot be reflected by simple mathematical terms. This is very important. Now, how we can model it? So we need to find the dependencies between the mineral prospectivity and the controlling data sets, means all these data which we have. And here we need this integration, data integration models. This is an algorithm presented by Carranza in 2009, and we are discussing this one now. And now we are here at what we do here in this company, or as we understand it. So we have our many, many data sets. We have the known locations of mineral occurrences, or where they could be or should be. And then we have still the geologist, of course, who has the understanding of what and why is where. And this is a very, very important thing here, to have this step before we are using the data integration models. So we extract from here, from all these data sets, we extract those parameters which are potentially controlling the location of a mineral occurrence. And then we take those as the input data to the data integration procedures, and then the algorithm creates the map showing probabilities or favorabilities, or how we can call it. But those are most similarities, means similarities of a piece of land to what we have used for training our models. Now, what is behind? Behind are mainly different mathematical algorithms, artificial neural networks, and other knowledge-driven approaches. And we combine them, as we have seen here. We combine them exactly here, where we put our knowledge together with the data. And we can do a qualitative modeling and a quantitative. Qualitative means we model where it could be. And quantitative means where and how much could be. So here we have the output is tonnages or something like that. And here the favorability, what could be where. This is a predictive map of gold in the famous greenstone belts of Ghana. And this is the Erzgebirge here, tin deposits near Alfredsdorf. So now here's an example of qualitative modeling, the American Massif in France, that was created 2017, almost 10 years ago. Here we have the controlling parameters, the histograms showing us how good is the model. It is a very, very good model. And with this model, we won a prize, a contest of BRGM 9 years ago. And this is an example of a quantitative model. Here, the density of manganese nodules at the seafloor of the Pacific Ocean have been modeled by using ANNs. So now about our software AdvanGeo, created here as the interface of artificial intelligence, geosciences, and data management. So this software integrates the entire workflow we have seen into one software shell from the data preparation up to the output of the results and the evaluation of the quality of the result of the calculations. And very good is that the software has a shell and all data is under it, so it can be taken and given away. And everything is repeatable because in the short time you create a lot of calculations and you forget what you have done yesterday or 2 days ago. But this software records it. So all this procedure is reflected in the software. So we have the supervised learning procedures A and N implemented in the software, unsupervised learning procedures or helping to analyze just relationships inside the data sets, not yet to a certain mineral deposits and certain mathematical frameworks, helping us to prepare the data. Now, how good the model is. This is a very important question, always asked. So we have here implemented our software 3 possibilities. One is the error curve. That means indicating how good the model is adjusted to the reality. So it's our histograms showing, analyzing the grid cells. All grid cells must have a very, very low value, and the yes points as possible high value. And then we have here an information of the contribution of each information layer to the result. So we can understand what the layer contributes and whether it makes sense or not. No, for instance, here's distance to certain rock types and so on in this model for the French Armorica Massif. A few examples. Here, our big project in Nigeria, which took us busy for more than 5 years. There is one of the main results is this metallogenic map of Nigeria, and behind this map is knowledge, of course, where is what, and then these middle potential maps created on behalf of the Ministry of Solid Mineral Development of Nigeria and now being used to attract investment to the country. Means for the different metallogenic domains of the country have been created this type of maps. For instance, for the basement here, gold potential maps, and for the platform or for the sedimentary basins, lead and zinc, and many, many more of these maps. Another example is here our Erzgebirge. We have this metallogenic map, the metallogenic scheme, and the mineral potential maps shown here for tin and spars. Now, yeah, how to improve it? There is a thing now in the last 3 years implemented with Beak, but not yet in the software, using Bayesian neural networks. The output of these network calculations is a likelihood, and the uncertainty means for each pixel of the map, we know the likelihood of something means here's the presence of a magmatic nickel copper deposit, or the chance to find it there, and the uncertainty of that information. What is now another step ahead of making the evaluation of the output of these calculations more reliable. And here we have this map. We have here a likelihood, and we here have the uncertainty, and means the reddish and yellowish areas here are those having the highest probability to find this type of mineral occurrence in the United States. That was a project executed on behalf of the Ministry of Defense of the USA 2 years ago. So now about Advangeo. Over the years, Advangeo became a bit, let's say, not outdated, but mostly because the Esri software was developed further, we also needed to develop our software further. So the main issue was to separate the software, the calculations, from the GIS. And this is done now. The Advangeo calculating core is separated from the GIS and can be connected to any GIS, especially also to QGIS, to free software. What makes it more applicable, especially for users who do not have the possibility to buy the expensive Esri software. We are going to implement more simple statistical preprocessing features, improve the user friendliness and so on. And by that, we are improving the user value and the product's appeal as such. So this new software is ready for sale in July and will be further improved with the QGIS extension, and will be further improved now by implementing very helpful data processing algorithms like analysis of geophysical fields and processing of geological maps and so on. And also integration with optical remote sensing data, and then the Bayesian neural networks, which are helpful to evaluate the quality of the calculation. So that's it. Thank you very much, and thank you to all my colleagues.